We have a guest speaker today, Viviana Acquaviva from CUNY City Tech. She's worked on a number of problems in astrophysics, including SED fitting for galaxies. Today, she's going to talk about galaxy separation with machine learning.
All right. Well, thank you. Glad to be here. I guess I couldn't get a good idea of what your background is. So please feel free to interrupt at any time. But also you can tell me to speed up if it needs be. I really don't mind. Okay, but I guess that, my understanding is that at least some of you come from a statistics background as opposed to an astronomy background. So I just want to give you my, one slide advertisement of astrophysics and tell you why it is awesome. So say that, you're your typical observer, which I'm not, but yeah, and you go out to your telescope, you look at the sky. Well, nothing happens, but you may happen to see that star, which would be, any guesses at what's the closest star? The sun, see? Hey, excellent. And so we see the sun because the sun is sending photons to us. Usually there are these little wiggly arrows. And they actually travel a pretty decent distance to get to us. It's a distance of 150 million kilometers or 93 million miles. And they travel at a certain speed, which would be, what's the speed? Of the photons? Yeah, the speed of light. That's why it's called light. And the speed of light is about 300,000 kilometers per second. So this means that in order to get from the sun to us, they take about 500 seconds. There's a distance divided by velocity. Usually I have to explain this to my students, so I'm willing to assume that you don't need that. This means that it takes them a little over 8 minutes to get from the sun to us. Now we can keep playing this game. Rather than the sun, we look at our closest galaxy. How many guesses of what that is? You're looking at her, but no. Milky Way is our galaxy, so very good. Yeah, no, it's true. So it is the closest galaxy, by all possible metrics. So I should say the next closest. You were right, yeah. Zero. Yes, distance zero or, a lot, because there are parts of the Milky Way which are actually very far, but still, So, it works. I'm afraid to say he is right.
I've coded a distance matrix a million times, so.
So what's the next closest galaxy? Andromeda, all right. Oh, yeah, no, I don't care about the small ones. These are satellites, I feel like that would be patronizing of us, too. So photons from Andromeda also take some time to get to us. And do you have any guesses of how far Andromeda is? That's a complicated one, so no. No, you guys can't answer.
I know we're not allowed to.
200,000 light years?
Oh, well, it's only one order of magnitude off. It's 2.5 million light years. So, even for our nearest galaxy, or at least large galaxy neighbor, is actually pretty far away. But you see that we have conveniently switched to this other unit of distance, 2.5 million light years, because this way we can immediately tell how long photons from Andromeda take to get to us. And what would that be?
2.5 million years.
Aha. And this is the whole reason why we have these units. So this means that when we are looking at Andromeda, the picture that we're seeing is 2.5 million years old, just because there is no faster way for information from Andromeda to get to us. And this doesn't really matter a lot for Andromeda, because as far as galaxies go, 2.5 million years is not a particularly long time scale. So probably Andromeda, in the picture that we have, which is this old, is still a good representation of how the galaxy looks like today. But if we keep playing this game with objects that are farther and farther away, what we actually can do is to look back in time. And we can look back in time almost all the way to the beginning of time, which is actually a concept, is the beginning of the universe, also known as the Big Bang. And I think, to me, this is the most mind-blowing fact. So in some sense, I think that it makes up for the fact that we can't really have experiments in the lab, because most of the interesting astronomical situations, things like, the inners of stars or galaxies, happen in conditions of temperature and densities that could never be recreated. And when we study the universe. We only have one of them, and I think this doesn't take that much statistics to know when you only have one sample, there are situations in which you can trust exactly that what you're seeing is not the consequence of having only that one sample. But how cool it is that you can look back in time. And so I always felt, okay, this is our consolation prize, like other sciences have the possibility of doing experiments and repeating experiments many times, but at least, we can do that. And so we
Can I just throw in that if anyone ever wants to learn how to observe, come on over to UNC Chapel Hill and you can help observe, and the galaxies in my survey are considered nearby by cosmic standards, and if you look at them, supposing that they developed dinosaurs at the same time we did, you would be seeing their dinosaurs.
Oh, that's nice. That's a nice analogy. So did you see any? Oh, that would be a spoiler. It's like, I can't tell you. I see, exactly. And then we zoom in and in and in until like a little dinosaur comes up.
Level zoom right there.
All right, so looking further and further back in time is something that we have done. And I like this picture because this sort of has a little summary of how far back in time we've been able to look by building bigger and bigger telescopes. Now, from my theorist perspective of what a telescope is, I'm sure it's more complicated, but I always just think of it as a bucket. And so, it's a bucket that collects photons. And so there are two ways in which you can collect more photons. You can build a bigger bucket, which in this case it would be like a bigger primary mirror, or you can just stay there with your bucket for longer, which corresponds to just having a longer integration time. And so we've done both of that. We've built bigger telescopes, and we just selected some patches of the sky at which we have stared for longer and longer. For example, with the Hubble Space Telescope, which just turned 21, we have some selected areas of the sky which we know really, really well. We call it we started as the Hubble Deep Field, and it became the Hubble Ultra Deep Field, and it just means that basically we have directed the same cameras but for longer and longer time until even the dimmer sources started to appear. So, oops, sorry. So I keep thinking that this is also a laser pointer, but is it? Yeah.
It is a laser, but it will not show up.
Oh, I see. Oh, the magic of physics. Okay. In this case, so in the 90s, we had ground-based astronomy. We still didn't have telescopes in space. And so we had observed galaxies which were, and here I'm saying something wrong, but I'm simplifying, say 6 billion light years away. And this corresponded to looking about 6 billion years in the past. The reason why this is wrong is that the universe is a dynamical object. So on large time scales, 6 billion years and 6 billion light years are not the same thing because the universe has been expanding in the meantime. But in order for us just to understand, we had been looking so far that we had looked at galaxies. We knew already that there were galaxies about 6 billion years in the past. And by the way, the total age of the universe is about 13.8 billion years. So this is really the temporal edge. We know that it exists. If we're willing to admit that the universe is expanding, then that there has been a beginning of time, because as you go back, at some point you're contracting until you get to a point. And this point is what we call the beginning. So if you're willing to admit that, then we know that there is a beginning, and we can calculate how long it's taken for the universe to get from where we are now to there, or if you prefer, when the right arrow time, it would be the other way around. And that's about 13.8 billion years. And then in 1995, we launched the Hubble, which is not a particularly large telescope. The primary mirror is 2.5 meters. So it's not the biggest that we have built by any means, but it has the great advantage of being in space. And being in space means that you don't have to worry about absorption from the atmosphere of the Earth, which actually tends to absorb all the radiation as it comes in, leaving you with very few windows. You don't have the problem of weather. You don't have any distortion coming from anything that happens between the object that you're looking at, or between this layer of atmosphere that we have. So it has multiple advantages, and you can use it 24/7. And then just by staring more and more at some patches of the sky, we have been able to see galaxies, what we call the first galaxies, like about 200 million years after the Big Bang. So I think that now this is like, we didn't anticipate being able to do that until like the next generation space telescope, which is this James Webb Space Telescope. But actually there has been like a recent detection of a galaxy which we believe is observed about only 200 million years after the Big Bang, or 13.6 billion years ago, which is amazing just because I don't think a lot of us would believe that these 200 million years would have already been enough for the universe to form a galaxy. Because you're starting from a state that is like incredibly hot and incredibly high energy. You can't even have atoms because they wouldn't stick together, given like the crazy temperatures that you have. And so it's like it's a relatively short time to form like things like stars and then like assemble them in galaxies and so on. So from my perspective, the main reason why I want to study galaxies, or I've started looking at these things, is because they exist for such a long time and they are so bright that you can really use them to, and you can take a look at galaxies across a range of eras, and you can answer a lot of questions about the evolution of the universe. You can tell whether like the first objects that formed were like big and then they like broke down in smaller pieces, or the other way around. You can tell whether like galaxies naturally form as spiral galaxies, for example, like our own Milky Way, or with other morphology, and how these evolve into one another. So there's lots of games that you can play. But I think the interesting thing is like really you can take a look across almost 100% of cosmic time. So now the galaxies that you see here, they are pretty and they have shape and colors and things like that. And I'm sure that the ones that Sheila has, because they're nearby, also offer a great amount of detail, right? You can see shapes, you can see structures. So these are the attractive ones. The one that I typically work with looks like these. They're just smudges. And this is because when things are really far away, even if you're looking at them with really good telescopes, usually the only information that you can have is not like the shape that they have, or you can't detect any substructure in the image. You really just have pixels, and all you can measure is the brightness in this like sort of little bunch of pixels that live close to one another. So how can you tell anything about these galaxies? Well, one thing that you can do is to look at them at different wavelengths. Right, so this is a map of our own Milky Way. And when we look at the Milky Way, because it's a disk galaxy, and we live in the disk somewhere, we can see our own Milky Way, but it looks like just a strip in the sky. We don't see it like the way that we see Andromeda, for example, where like we are like looking at it from far away, and it's not quite edge on, but it's like with a certain inclination, but we can see the structure. Looking at the Milky Way just means that we see this like stripe in the sky. But this is how the Milky Way looks observed at different wavelengths. So this is radio, this is infrared, this is near infrared, this is optical, where you have like dust obscuring all the stars that live towards the center of the galaxy, and so dust absorbs optical light, and that's why you see these black lines. This is gamma ray, this is X-rays. So the Milky Way looks nice, and that's because you're looking at an image, and each pixel of that is representative of the brightness in that particular wavelength. But for less fancy data, what we do is we build these things called spectra, which are just a chart of the galaxy luminosity, or brightness, I should say, because if you don't know the distance, you can only talk about brightness, as a function of wavelength. And so here, when you have something like a spectrum, you have basically a measurement of how bright the galaxy is at all these wavelengths, and you have these like special places, special spikes, where the galaxy is brighter than average. So far, so good? Okay. So do you know what the spikes are? Okay, great, because I feel like, am I boring them with things that, like they've heard like a million times? Okay, great. So the spikes comes from, they're called emission lines, and they come from electron transition between different energy levels of common elements like hydrogen and oxygen. So I don't know if you've seen like the Bohr model of the atom, which says, okay, like which is, as we know, it's kind of wrong, it's a simplification, but it works to understand like a bunch of these things. So in the Bohr model of the atom, you have like the nuclei, we have particles like protons and neutrons, and then you have electrons that are like running around. And we've learned from quantum mechanics that these electrons actually are not allowed to orbit the nucleus at whatever energy they want. They are only allowed to live in some like special energy states that correspond, in this simplification, this corresponds to specific distances from the center of the atom. And for each element, hydrogen, oxygen, neon, whatever it is, you can accurately predict what these energy levels would be. Now, when a photon of the right wavelength comes, atoms are able to absorb this photon, but only if the photon has just the right amount of energy to correspond to a jump between one energy level and the other. So for example, the hydrogen atom, which is the simplest one, only has one proton and one electron. This electron has a number of energy states in which it can exist. So normally it would be just, like hanging out in the like lowest energy state, just like we do. In general, nature always prefers the lowest possible energy state that you can find. That's why, when we sleep, we want to be lying down as opposed to here, because that's like a lower energy state. And in general, like everything in nature follows this principle of minimal action. So, it seems like silly, but it's actually really true. That like the rest state of an atom will be like the lowest energy possible. This corresponds for the electron to be as close as possible to the nucleus. And then, if like many photons can fly by, and the atom wouldn't care. But if you have a photon which has exactly the energy of this jump, then that photons can be absorbed, and the electrons can jump up to its second excited state. And it will stay in this excited state for a while. After a while, it would tend to actually go back. And this corresponds to the emission of a photon. And the photon that is emitted also will have exactly the same energy of the jump between the first and the second level. And so if we go back to our spectrum, which I guess we also have here, you see that these spikes just correspond to emission lines, meaning like jumps, in common elements. So you have like the ones of hydrogen, there is like the H alpha line, which is like one of the hydrogen atom transition. You have the H beta line, the H gamma, and the H delta. These are lines that correspond to jump from different energy states to the second one. Then you have the Lyman alpha line, which is not at the right wavelength, so it doesn't appear in this spectrum, but it's one of the strongest because it's the very simple one from level 2 to level 1. And these are pretty strong just because in the universe, hydrogen is by far the most common element. So this is something that is very different between, like, say, a planetary system like the Earth and the universe. Like on the Earth, what's the most common element? Well, it's hard to tell. Let's say in the atmosphere of the Earth.
Nitrogen.
Nitrogen, right? It's like 78%. What's the second? Any guesses? It's one that we like.
Oxygen.
Oxygen. So, and how about the crust? Well, carbon, there's some of it. It's not the most common, I believe.
Iron.
Iron is a lot of it is in the core because it's like sort of like heavier, so it's there. Oh, it's silicon. Not an element that we actually think about a lot, but it's common. But usually the distribution of elements like on the Earth or in any planetary system is very, very different from what happens in the universe. The universe is really like 99% hydrogen and helium, because these were the elements created by the Big Bang, basically, and then in a lot of places nothing else happened. So like our Earth is actually a very, very special place in terms of like density, environment, and composition. In the universe, if we look out there, we are much more likely to find emission lines that come from hydrogen just because there is just so much of it. And so you see that the emission lines that you see in a typical spectrum will come from, this is from helium, we have like the hydrogen one, you have oxygen, you have nitrogen, and well, this is argon, this is like neon 3 to a smaller extent. So when we look at a galaxy and we try to get a record of how bright the galaxy is at different wavelengths, and if we can actually sample this really, really finely so that we have information not just like in sort of like in wider bins, but at every single wavelength, then we build something like that. The part that represents the average is called the continuum, and the spikes are called emission lines. And this matters just because the survey that I'm going to be talking about actually uses this technique to find galaxies. So now, because we can actually, like I lied when I said, hey, in the lab we can't recreate these. One thing that we can do well in the lab is to observe the wavelength at which this transition happens, right? We have hydrogen, we have access to hydrogen or oxygen or nitrogen, so we can go in the lab and we can say, okay, let me sort of like have a lot of photons going through this gas, and then you can measure the wavelength of the transition. So it looks like you would know exactly where this transition happens. And so when you see them in a galaxy, you should be able to tell, oh, okay, this is oxygen 3. It's happening at a wavelength of like 5,000 angstrom and change. Right? So it seems like, okay, then if I have like a spectrograph and I can look at a galaxy and I find an emission line and I look at the wavelength, I can tell exactly what that emission line is because I can repeat the experiment in the lab and measure for every transition at which wavelength it occurs. So far, so good? Yeah?
How often are you able to sample this densely to get like a nice curve that looks like that?
It's not bad. I mean, like we have instruments called spectrograph, in which case we can do it. The problem there is that if you actually want information about the brightness of a galaxy, like such finely sampled, you need a lot of integration times to get to a decent signal to noise. So this is like relatively easy to do for things that are close by, but for things that are far away, the answer is like much less often than we would like. And this is like one of the huge problems that we have, that spectroscopy in general is expensive because for things that are far away, in order to get a decent signal to noise, the integration times like blow up, and this is a problem. So we're always trying to find the trade-off between how many objects do we want to observe, or just being very careful in the selection of the targets because it's difficult. So it looks like So
what did you say about the Lyman alpha? Lyman alpha?
Yes.
So is there anything called Lyman alpha blob?
Yes. So these are sort of like extended structures where you have Lyman alpha emission. And and actually Lyman alpha emitters is like one of the type of the galaxy, but I'm talking about the sort of like a point like emission like in the position of the galaxy, and I think like Lyman alpha blobs are sort of like this extended structure where we see like enhanced Lyman alpha, and you like to understand physically what kind of regions they are or where they occur. So the problem that we have, in sort of like measuring emission lines at certain wavelength in the spectrum and associating them with like the physical elements that produce that emission line is the fact that the universe is expanding, and this produced the so-called Doppler effect. Right? Just as a reminder.
Oh, he's the Doppler effect. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
So far, so good. Have you heard about Doppler effect? Okay. So the Doppler effect, I don't know if you guys are familiar with the Doppler effect in the universe. Usually we hear the Doppler effect when we have, I don't know.
Something drives by you.
Right, something drives by and the frequency changes. Right, and in this case, this is like a change in the frequency of an acoustic waves, which travels at the speed of sound. And the speed of sound is much lower than the speed of light. So of life, yeah, it's very existential. But no, than the speed of light. So in general, this is also supposed to happen to, I don't know, like the sort of like the color of like the headlight of a car, if it's driving towards you. But because it's such a small change in frequency, like the velocity of the car compared to the speed of light, usually we are not familiar with the effect, with the Doppler effect applied to light as opposed to applied to sound. But it does make a difference, and I have another little video that I like about this, so I'll just play it.
observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our Doppler electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see.
Oh, sorry, you're right. Okay? Okay, so this is like the effect that we have. So this means when we go back to our spectrum that a spectrum that has been emitted by a galaxy that is far away means that this galaxy is actually moving away from us at a very high speed, because the expansion of the universe happens quite fast. Speeds are comparable, or even larger, I should say, than the speed of light. The speed of the expansion is proportional to the distance of the galaxy. So the farther away galaxies are, the faster they're moving away from us. So when you apply this to a spectrum, this means that every spectrum of a nearby galaxy has been stretched, and as the spectrum stretches, this emission line shifts. And they may be observed at a wavelength that has nothing to do, or actually I shouldn't say there's nothing to do, but it is much, much larger than the wavelength of the actual emission. So here I have an example that actually comes from what you're seeing here are two spectra, but actually it's the same spectrum that just has been stretched. So the model galaxy, in this case, it would be the same, but I have placed it at two different redshifts, meaning at two different distances from Earth, and this corresponds to one like moving at a certain speed, and the other one moving at a much higher speed, so with a much larger Doppler effect. And what is happening here is that the top spectrum, like say that this is our detection of emission line in the spectrograph. It is observed at a wavelength that is, I think, like just below 5,000 angstrom. But this is to show you that it could come, like this emission line, when I see it, I just measure a spike here, so a flux in my spectrograph with a certain signal. And it could be, say, an oxygen 2 line, which lives at a rest frame wavelength, which I would observe in the lab at 3727 angstrom, associated with a redshift of 0.3. Or it could be a Lyman alpha line, to go back to our favorite, which is like a very strong line. And you can see here that, like the emission line is actually very strong compared to the continuum, which is like the average brightness of the galaxy. The Lyman alpha line is naturally emitted at 1,216 angstrom, but if the galaxy is much farther away, in this case a redshift 3, this wavelength gets to be multiplied by 1 plus c. This is the stretch factor, and so it will be observed at the same wavelength. So the bottom line for that is that this is all I know from my spectrograph. I see a spike at the wavelength of, say, 4,900 angstrom. Who tells me what that line is? Nobody, right? So, like in general, just by looking close by, you are able to exclude some other types of contaminants. But the problem that we have for this survey in particular is we want to be able to tell whether we're looking at a faraway galaxy, which is a redshift like, between 1.9 and 3.5. This is like the range of the spectrograph for which like the emission line would fall within like the observable range, or an oxygen 2 emitter at much lower redshift, between like 0 and 0.5. Does it make sense so far?
So is the green spike, was that on the blue spectrum, but to the left of where we can see?
In a rest frame? So what I'm saying...
So the green is a shifted version of the blue?
Yeah, this is the same spectrum, shifted with two different stretch factor.
Okay.
And what I'm saying is like, this would bring the oxygen 2 line that, like at 0 stretch factor would be at 3,727 angstrom. Like it's taken by this small stretch factor to like, I don't know, 5,000. And then, or, you could have like a Lyman alpha line, which lives at 1,216 angstrom with a much larger straight factor, and they would end up seeing exactly at the same wavelength. So, and when you see it, of course, you don't know what line you're looking at. Like all you see is that you observe, like say that this is like the range of your spectrograph. Most likely, this is like the detection threshold. And so you would see nothing, 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 because the continuum is below the detection threshold in most cases. And then you see like, OK, this is a spike. And then nothing. And so, unless you have additional information, you don't really have a way of telling whether you're looking at one emission line associated to a certain stretch factor or the other. So this is the problem that we are facing in this survey that I'm part of that is called HETEX. It's an awesome survey that will use faraway galaxies to study dark energy. Now, have you heard about dark energy? Well, dark energy is like really weird thing. So about 15 years ago now, no, about almost 20 years ago now, we discovered that the expansion of the universe is not just a thing. I mean, we knew that the universe was expanding, and we had been accepting that for a while. And we decided that it would be nice to actually find out what's the matter content of the universe. This is because, like, from all the discussion about dark matter, which is yet another thing, we had lots of indication that the amount of matter found, like, in stars and galaxies is not alone enough to justify, like, the dynamical things that we see. And so some very smart people had this idea of saying, hey, you know what? The universe started expanding at some point. So there was an initial momentum of this expansion. After that, the only force, the only long-range force that we know of is gravity. And gravity would actually slow down the expansion. So, and like the more matter you put in the universe, the more gravity you expect to have. So like the slower you imagine your expansion to proceed. So given that we can measure how fast the universe is expanding today, we figure, okay, if we can actually find out this deceleration rate, this would be a really good way of weighing all the matter in the universe, because we can see, okay, what's the mass that corresponds to this deceleration factor? So we did that, and actually there were like two competing teams who did that, and we found out that the expansion of the universe indeed is accelerating, which was extremely unsettling. And in fact, I am very glad that there were the two competing teams who got this weird result, because otherwise it would have taken, I think, a lot longer to become widely accepted. But this sort of we were quite at a loss with this observation, because really we don't know of any type of matter or any type of force that could have this effect. And the somewhat obvious answer of anti-gravity, which means just like the electromagnetic force could be either attractive or repulsive. So I think it would be easy to think, oh, okay, how about gravity? Can gravity become anti-gravity? Negative gravity in some regimes. But unfortunately, while all the forces are associated to some property, for example, the electromagnetic force is associated to like the electrical charge, or gravity is associated to mass. These things are like the carrier of this particular interaction. This acceleration seems to be observed everywhere with no regard for what's in there, for the density of the environment, for the temperature, for the mass, or any property that we could think of. So I don't think that we know what that is, but one thing that we've done in the past 15 years or so is to collect data And the data now seem to favor something called a cosmological constant, something that would be sort of like a vacuum energy, just associated to like space-time, if you will. The value that the universe has chosen for this vacuum energy is very, very weird in the sense that on dimensional arguments, you could calculate what that value would be expected to be, but the one that is actually measured is about 120 orders of magnitude smaller. So to many, this is not a satisfactory solution, but from a phenomenological point of view, if you just add one number to the equation describing the expansion of the universe, and this number is just like a constant in the energy balance of the universe through time, you can actually explain everything that you see on large scales. Because, as I was explaining, this is quite unsatisfactory, we have decided that it would be interesting to have survey that can tell us about this dark energy, whether it existed, whether it was relevant, how much of that there was, in a time that has not been explored. And this is the goal of HETEX, is to look at in sort of an era of between, I would say, okay, this is the Big Bang, this is what we studied, this is where we want to be. So I would say between, actually 2 is 3 years, between 11 and 13 billion years in the past. This is a regime in which we actually don't expect dark energy to do much. We expect it to be very subdominant. But because we really don't know what it is, we think that, like you can't actually, after all, we didn't expect it to find it in first place. So I think it makes sense to try at least to collect clues on, whether we have any hint of evolution with time or whether we see any surprises in the relative abundance of dark energy and other stuff. So we're trying to do that, and to do that we are using these galaxies. But you can imagine that we have, it's really crucial that all the galaxies that we are selecting in our survey are the ones that are far away. If these like nearby contaminants, which were like the green galaxies in this plot, sorry, the blue ones, we want to have like galaxies like the green one, the one that are far away, because in this case we will be selecting the Lyman alpha line, and this is how they are found, and want to make sure that no one of the nearby objects for which we are like mistakenly looking at our emission line and thinking that it's Lyman alpha, but instead it's oxygen 2, make our survey. So the first things that we did is, one pretty dramatic difference between these two spectra is the level of the continuum. Right? So in this sense, galaxies that are far away are also less bright just because they are far away. So on average, they are seen from, like a distance that is, well, I don't know how many times, but I think it's like, I can't remember what is a factor, but like the brightness, the apparent brightness of an object varies with like the inverse of the squared distance. And so things that are farther away, of course, will appear dimmer. So if rather than just the line, we can also measure the continuum. We can, this gives us some information on whether the galaxy is nearby or far away. And sometimes, I don't know if I have a definition of jargon, sometimes one quantity that we use is something that is called equivalent width, which is the ratio of the flux in the line divided by the average brightness of the continuum. Right? So for galaxies that are nearby, like the blue, the flux of the line divided by the continuum will be a small number. For things like the green, the flux in the line divided by the continuum will be a larger number. Questions, comments? We're good? Okay. All right, so this is the problem. So basically we have our data, and in this case the data are quite simple. We have the continuum measured at in a few bands. we have the spike, like the strength of the emission line, and another thing that we actually have is the wavelength of the observation. Just because, it's possibly, we thought that this was a relevant feature because it's possible that, where this lies in the spectrum, like maybe like for faraway galaxies, it can be like, it would be uniform in the range of the spectrograph, but this one won't be. We tend to see these oxygen 2 emitters like on the red side, like sort of like on the right side of the range of the spectrograph as opposed to on the left. So where the detection actually happens is also a feature.
So you can't see the continuum in the spectra usually because it's below.
Yes, and so you have
but
to.
But you can see it with some photometry.
Yes, that's the idea. So the idea is to basically have a photometric follow-up, on which maybe you just measure the continuum in one band, but because photometry is less expensive, you're just looking at an average over a range of wavelengths, the integration times required are much lower. And so this is a way, we are expecting to have continuum, at least in one band, for the whole survey.
Okay, and you would have that filter be for wavelengths near where the spike would be.
Right. The range of the spectrograph, I have it here. I don't have it here, but it's a range. It's a relatively limited one of like several hundred angstrom. And so, in one filter, you can actually have that. Like the range of observed wavelength will be like covered with one filter. Actually, it's between, or actually, we have discussion. So it's either G or R that you want. Like, it wouldn't be like centered. So, you will leak a little bit of signal on either side, but it's either G or R filter, so either green or red. Okay. So this is the problem.
Sorry.
Yeah, no, please.
You just don't get a spike either. You would just have just the photometry and the knowledge that there was no observable spike, or is there?
Well, it's a blind survey. So, what we do is like, the observation are carried with a spectrograph. And then only when you have a spike, only when you have detection of an emission line, then you will have like a follow-up photometry. So there are cases in which you have the spike, and then you can't find photometrically any objects associated with that, which will be an issue, but not the other way around. Because you wouldn't have a reason to go and sort of like have a photometric observation of a place where you didn't have a spike in.
Probably there's nothing there. There's no spike.
Yeah, right. You didn't detect a spike, right? So you have a detection threshold in the spectrograph. And that tells you, okay, these are all the candidate emission line objects. And these are the locations where you will go and do a photometric follow-up. Yep.
So dark energy, amount of dark energy, is it constant or is it increasing kind of thing?
Oh, it's constant, but what is increasing is the relative amount of the dark energy compared to the other forms of energy in the universe. And that's why it became dominating. So what happens, is it okay if I go to the board for a second? I'm okay, also not. So the idea is like if you look at the different forms of energy in the universe, and this is time, right? You have that the density of the energy of other things, usually like there are three things. There is this dark energy that will live here for a second. And it's just constant through time. Okay? Then you have two more things. You have radiation, basically photons, and you have matter. Okay? So when you look at matter, like, we can think about ordinary particles, right? And so if the number of particles is constant, then this means that as the universe expands, the density will be proportional to, let me call it a sort of like any like linear side of the universe, any dimension. It will be proportional to the inverse volume. No, right? Yeah. So it will like decrease proportional to the volume. So if the volume expands, the density decreases. And if rather than the volume, I use this like a scale factor, just to say like any linear dimension, this would move as a to the -3. And this is how the density of matter evolves. And then the other things that you have is radiation. Radiation is expressed in terms of photons. And for photons, you have like two combined effects. So the density, the energy density of photons is proportional to, you have a factor of 8 to the negative 3 that comes just from the volume. So they are like volume density is decreasing. But also photons, they stretch. And this means that they lose energy because, you know, like a photons is like a wave. And so when you stretch the wave, they go to lower wavelength. Sorry, it's to longer wavelength, lower frequency. And the energy of a photon is just like h nu, h times the frequency. So it's inversely proportional to the wavelength. And so the radiation density actually decreases more rapidly, like a to the negative 4. So in the history of the universe, you start, you know, if you sort of like reverse that. So that you have like a steeper curve that is rho radiation. Then you have a less steep curve that is rho matter. And then you have this like dark energy, which is constant but lurking here. And so no matter what's the relative amount that you put in the beginning, you see that you start with a radiation-dominated universe. Because when the scale factors become small, then this number becomes very large, right, as you go back. And so you have a beginning here where you're radiation-dominated. After a while, this is decreasing more steeply, and so what like comes next is a matter-dominated era. And here we had that. And in all this, dark energy is constant but completely insignificant. But you know, no matter how much you have at the beginning, you're bound to get to an era where, because the other two decrease, and dark energy is constant, where this is going to become important. And in this one, we think that this happened at the redshift of about 0.5, if I'm not mistaken, the equality between the two. And now we are actually in this regime where this is about 75% dark energy and this is about 25% matter. And radiation is completely insignificant at 10 to the negative 5 level. So
you are considering the curve of the densities, right? Not the matter.
Say again?
So those curves are for the densities?
Yes, the energy densities. So when you know, if you want to write the energy balance of the universe, you can write it as the sum of these three things.
Yeah, but you are considering density, not the matter, right? Density of the matter, that means the amount of matter is constant always. Right,
the number of particles is constant, but the density decreases proportionally to the volume, to the inverse volume.
Dark energy is not decreasing.
No, that's the weird part.
The density of the dark energy should be decreasing.
No, it shouldn't. It's just like if it's this cosmological constant, it's okay for it to be constant. This is just what it is. It's weird because it seems to violate energy conservation, right? But it's like, that's why we're saying it's a property of space-time. So you can't explain it in classical physics. You need general relativity, right? Otherwise, you will have to say that, okay, you know, if the total energy of a system is constant and the system expands, then, you know, like there's no way that the energy density of anything can remain constant. But if you have general relativity, then you have like the equation gets modified in a way where there is an interaction between the energy density of the stuff that is in the universe and the structure of the space-time. And this is called like covariant derivative. So we say that now the energy of a closed system needs to be like covariantly conserved as opposed to classically conserved. And this makes things okay. So it's not violating any fundamental law. It's just weird that it would have, I think, you know, there's different things that are weird. The value itself is weird because it's very small. And the other things that many people find weird is that if you look at the evolution of the universe, in most times you have the one form of energy density is completely dominant. And we are in these like weird times where actually these two are quite comparable to one another, 75-25. And some people also find this weird. I don't have a specific opinion about whether this is weird.
So that means that at the time of Big Bang, the dark energy was also 75% of.
No, because look, like the abundances are the ones that you see here. So you see here, dark energy was the same amount, but radiation density was much, much, much higher. And so this was completely dominated. and this was negligible. Then you have like a following part where now radiation density doesn't matter anymore, but you are like in matter domination, so matter is the one that counts. And only recently, and by recently I mean the last few billion years, we have dark energy domination. And so now what we are trying to do with this survey is basically to go and look at this regime where dark energy is supposed to be, actually maybe even a little further up, where dark energy is supposed to be considerably less than matter energy density, like we're looking at 1-2% level, and we'll see if we can find the detection there. So that's...
and where is the dark matter? Dark matter is also constant, or?
No, the dark matter is included in this, and so we don't know what the dark matter is, but we are just assuming that it behaves like regular matter in the sense that it's just like particles, just particles of like a different kind that we still don't know, and so that it evolves again, you know, like the matter, dark matter and luminous matter density, they both like decrease with the volume. Nice. I don't get to talk about cosmology nowadays very much, but this is where I started. So, you know, like for several years, I've actually studied like phenomenology of dark energy and gravity models. And then I was like, well, we have no data, so bye. And now actually I think we're getting more data. So I'm hoping that there will be like a renewed interest in this kind of stuff. But anyway, to go to our more mundane problem, we have this data. And we have to find a way to say whether the galaxy that we're looking at is an LAE or NO2 emitter, right? So it's this classification and regression model, like for you guys. What type of, right. And you know, I'm talking about this now because I sort of want to look at it from a different perspective a little later. Okay, so we've actually looked at that in two different ways. The first way was to sort of write a formula. And in general, this is like a rule or, you know, a likelihood function that tells you whether the galaxy is red or green. So we wrote a paper called, like, you know, sort of just applying basically Bayes' theorem to our beliefs on the distribution of these two types of galaxies in the universe and using that to make this classification. I won't be talking about that. The second things that I will be instead mentioning is using machine learning. So in this case, we need a training set for which the output is known. And, you know, actually, even if we don't know anything about the physics, we can make a prediction. And so the idea for us here is that we're going to have a follow-up experiment in which we are going to look at the continuum, but in several different wavelengths. So rather than having only like a one band, so, you know, sort of like a generic thing of, okay, you know, what's a continuum close to the line, we're going to have like a better spectrum, like a better sample spectrum with photometry though. And this, like, from, you know, if we have information about the global shape, then we should be reasonably sure of what our labels are going to be. And from there, you know, we're hoping to be able to say, okay, this is like my slide where, you know, I try to tell people our brain machine learns, like, you know, if I put another point here, you are going to be able to tell whether the next one is green or red. And this is my usual response to, you know, people who tell me, oh, my machine learning is just like a black box and you don't understand anything. And instead I think, you know, it's just sort of like a different coding up of something intuitive. And as I'm sure you're aware, but I repeat just in case, the accuracy is limited by the size and the quality of the training set. So in general, this is the problem that we have, making sure that our training set is good enough that it's an unbiased representation of the global set of objects that we want to use. So say, for example, I give you this training set, and you have, you know, we have two objects for which you know the rule, input is 1, output is 3, input is 2, output is 3, input is 3, output is 3. But that's not the case, otherwise it would be too simple. And so this is a case in which, like, the training set that I gave you was poor both in size, it's only 2 examples, and in quality. I can actually do better. Now suppose that I give you this data set instead. And now you see that the 2 examples, the first 2 are the same, but I've added 3 more. So for input 3, output is 5. For input 4, output is 4. For input 5, output is 4. Anyone wants to predict what's
3.
and why?
Number of levers.
Right. See? Amazing. So this is telling you, well, hopefully, that first I wrote the input data set in a way that was more friendly, like, that was more meaningful, because now I spelled out the names. And second, I've also gave you like a few more options, a few more samples that you could use to infer what the rule is. And so, we've been thinking a little bit about that. So I'll just go through this machine learning jargon, although, it may be redundant for you guys. But basically, for me, the features will be the quantities that are observable for all objects. And so in this case, they're quite simple. There's only 3 of them. Continuum flux density, the emission line luminosity, and actually, no, there's another one, the wavelength, and the equivalent width. The equivalent width is really just the ratio between these two, but I've seen that it makes somewhat of a difference, and it's like a more physical things, because large equivalent width is generally associated to my like faraway galaxies, the ones I'm looking for, and lower equivalent width is usually associated with DO2 meters, the ones that we want to get rid of. And we're assuming that the labels LAEO2 are known for like 10% of the objects. So we've been running simulations. So far, everything that I'm going to show is on simulations that basically we have a total of like 1 million objects or so, and we are assuming, and we think so, just from like the ancillary data from the survey, we think that we should be able to have labels for about 10% of the survey.
What produces the labels?
Having like multi-wavelength photometry so that we can get like a photometric redshift.
How
So-
are, sorry.
Yeah, no.
How are those chosen? Like you end up with 10% label, but are those like random 10% out of the whole set? Or?
So for these simulations, yes, I'm just assuming that because this is like simulated, so also the catalog is simulated. It's simulated with, we hope in a realistic way, because we used what we think are like the sort of number density distributions of these galaxies at the redshifts of interest. And so we are populating our catalog with something that we think is physical. In practice, I can show you where they come from. Let me see if... no, it wouldn't be here. I think it was in the talk that I gave yesterday, so that would be called UNC. So this is the footprint of the survey. These are like the red areas. And so you can see that there's a bunch of other surveys that just overlap. And so in particular, like in this particular region, you have this like Sheila, this actually cases survey, and the dark energy survey is the yellow, and then you have like a whole bunch of other data. And in this one, you only have the G-band survey. This is like our own continuum that will happen for everything. But this is a region in which you have like multi-wavelength data. And so, you can argue whether or not they are independent because they are in contiguous region. But I think like from a perspective, this is like, the total of the survey is about 420 degrees. So we'll have like data for, I think, a region of the sky that is large enough that I wouldn't be too worried about like sample variance. But in some sense, in real life, we don't really choose the object for which we have labels. We're just going to use other surveys for which there are multi-wavelength data so we can have reliable photometric redshifts.
So the bottom is a separate area?
Yeah, there are 2 areas on the sky, like a spring and fall field. They have like completely different declination. So this is like a northern part, and this is an equatorial strip.
That's stripe 82?
I don't believe so. Oh, yes, so stripe 82 is the this one, it's the purple.
Okay.
Yeah. Okay, so let me go back to my other one. Okay, so my other problem was how to pick an algorithm for this classification. Do you guys have suggestions? Or what would you do to decide?
Well, you have 4 features total.
I only have, 3 or 4. I used 3. Basically, I selected 3 out of 4, so not many.
Simplest possible thing would be to build a classifier off of like a regression or some kind of regression tree.
Yeah, I'm listening. I don't know. I don't have a right answer. Like so.
So like a lot of kernel methods don't work well in high dimension, but they work reasonably well in low dimension. So it's 4 features, things like making a kernel density estimate for each class, and then doing a likelihood ratio.
Oh, I'm open. This is like, it's not.
I've never seen the data though, so that's.
Yeah.
It's not a good idea to give advice on it.
No, yeah, it's true. But I mean, this is just sort of, like for us, like things to, So is
this not the, sorry, is this not the sort of thing that people do with like support vector machines?
Right, that's what I used. And I've tried a couple of other things, but I was actually generally interested without, biasing anyone in hearing if there were like other suggestions, just, given the outset of the problem.
Well, James taught us about random forests, but you didn't like that for this?
Well, I don't know. One thing that random forest and support vector machines are sort of good at is if you have a lot of features, they can kind of figure out which ones are important. And there are other methods, usually like non-parametric methods, which they don't do so well when you have a lot of features, especially when you have a lot of like useless features. But they can potentially do a decent job if you have a lot of.
Decent job being better than SVM?
Well, it's hard to really. I mean, every problem has its own like best method. So certainly kernel methods would not do well if you were in the high dimensional setting where you have like 50 features and a bunch don't work or a bunch are useless. But in a situation like this, some of the kernel methods might at least be something you'd want to try. Like I wouldn't even try kernel methods if I had 100 features and I had no idea which ones are good, and probably only 20 of them are good. They would definitely fail.
Yeah, so I agree. So my line of thought then I found this. So I thought it's kind of like fun to show. But like my line of thought was my understanding of like ensemble classifiers is that they're useful when you have may have like a bunch of noise, either like noisy features or like noisy examples that you want to sort of like get rid of. In my case, I actually, especially because this is like a simulated catalog, I thought like that. My reason not to use for not wanting to use support vector machine may be just that they are a bit slower, but I thought that in this case, I thought that they could work quite well. And then, I don't know, I found these, which I haven't actually used, but I thought it would be sort of fun to like, try to use it and see. This is, well, I have it, like I use scikit-learn in Python as like a machine learning package. And
is it from their pages?
Yeah, it's somewhere on their, I don't know if it was like a blog or, but I think because like, the most frequently asked question was, what algorithm should I use for my problem? Then, they put up this sort of like cheat sheet. So in this case, I would say it's kind of funny. It's like start, you have more than 50 samples, no, get more data. But then it would be yes. In this case, I am predicting a category, so it's like classification. So yeah, do you have labeled data? Yes. Do I have less than 100K samples? Yes. And the first suggestion is linear support vector classifiers. So I actually felt quite happy with my own algorithm selection. But yeah, although I'm actually using RBF kernel, not the linear one. But yeah, I don't know, it's something like, fun to have, I guess, if you're like starting out with a problem. Anyway, the the algorithm that I've been spending the most time optimizing has been support vector machines. And so this is just sort of an idea of how the data look like. So as I mentioned, in the end, we end up using 3 features. And so this is just, it's a plane. So there's only like 2 of them that you're seeing. But basically, this is the continuum, right? Like the sort of like average brightness of the galaxy on each side of the spike. And this is the equivalent width, which is the ratio of like the flux in the line to the average flux in the continuum. So, and what they had done for their survey, like, before we sort of started looking at that, was just to sort of like draw a line and say, okay, everything that is above 20, that has equivalent width above 20, is going to be a Lyman alpha emitter. Everything that is below 20 is going to be an O2. And when you look at the data, you see that this works, up to a point. But first of all, like the first thing that you just want to say is like, hey, how about tilting the line? And this is because this limit in equivalent width is something that will change with redshift. Right? Not all objects are at the same redshift. So basically, you will have sort of like the same physical separation in true equivalent width, in true strength of the line, but this will change with redshift because the strength of the line and the continuum will change with redshift. So, at the very minimum, you just want to take this line and tilt it. But then we thought, okay, we think that it's possible to do a lot better. And so, I set up with this support vector machine. And I mean, the idea that I gather you guys are all familiar with is that what you do is you want to map your data into a higher dimensional space so that, each instance is, they become more separated. And then you want to find the hyperplane that maximizes the separation between the 2 classes, which will be the decision boundary. So the hyperparameters that you can play with, like at least in the very beginning, are the kernel, which is, I guess, like my best description. That is the functional form that describes the shape of the boundary. And so a linear kernel is, well, not surprisingly, a line, or like in higher dimension, it would be a hyperplane. But then you can sort of like, use different kernels. I actually use a Gaussian one that becomes like more or less wiggly. So there are definitely cases in which like your 2 classes may be distributed like in a curvy shape, and so you're not going to go anywhere with a linear boundary. But if you have something that looks more like a circle, it would work a lot better. Then you have, for a Gaussian boundary, which is not shown here, but it's actually what I'm using, you have gamma, which tells you sort of like how featureless your boundary is. So a lower value of gamma corresponds to something that looks more like a line, and the high value of gamma is something more wiggly. And as you can see here, it's usually here you may have like worse classification performance, but here it's easier to overfit because you may actually give your boundary a lot more featured than what are really there. And then you have C, which is like the soft margin, which is basically a penalty associated to misclassification. So you may want to choose whether your support vector lies closer to the boundary or a little farther away. And this will basically give a different weight to things that are misclassified on one side or another. So these are the sort of like vanilla things that you can play with. So here what I did is like take my learning set. So I started with like a simulation that had like 10% of the total objects, using 80% for training and 20% for test. And I did like k-fold cross-validation on my training set to find the hyperparameters. And then I reserve like a 20% of data, which I've never been part of the training, to sort of estimate the performance once I found my optimal estimator. And I've had, I'm still not 100% convinced that I'm doing the right, or at least like the best things here. So, I would definitely be happy to hear suggestions if you have them. But the idea here is that I do a model parameter search, I think.
What's the difference between a learning set and a training set?
So the learning set is all the objects for which labels are available. But I don't want to do training on all of them because I want to reserve a part of that for which the label is known just to check how my algorithm is doing. And I don't want any of them. Yes. So yeah, I don't want any of them to ever have been part of the training process. So here I'm just basically taking like, the idea of like k-fold cross-validation is that in order to evaluate sort of the best model parameters, so in this case it would be like the gamma, the soft margin, and the type of kernel, and something else. You don't want just to pick one possible split in there, but you want to do it multiple times, and then I take the average performance of the algorithm over these, I can't remember if I like 4 or 5 folds, and I select the parameters corresponding to the algorithm that on average gives me the best performance. Make sense? No complaints? Okay. So where does the human factor come in? Hopefully somewhere, because we don't want, I think, if we can just like, take anything and just like plug and play, then I think there's no point in keeping doing science. And so I was like happy with myself in knowing that, you still have like to think about your problem. There are ways beyond the standard, okay, let me do a grid search for parameters that actually matter more. So the first thing was to pick I thought I had put some like fancy animations here so that you wouldn't see everything at the same time. But anyway, so the first one was like, what to use to estimate the performance of my classifier. And so I think like the standard things that you find in scikit is like it would report the accuracy of a classifier. But this is not necessarily a meaningful thing. So have you heard, I don't know, like I heard of it as the accuracy paradox, but I don't know if in the world of statistics it's, it even makes sense or is known. Well, so, if, let's say that we use accuracy to estimate whether or not our classifier is doing well. So accuracy is really just the percentage of correct prediction. Like what are like if, once I choose a positive class, so in general in my examples, Lyman alpha emitters are my positive class, accuracy would be like the number of true positive plus true negative divided by, the total number of objects, however they are classified. So if the data set is not balanced, what you have, say for example that like 99% of objects are in one class, you can build a completely dummy classifier that puts everything in one class, and you will have a 99% accuracy. But of course, this is like deeply unsatisfactory from a physical standpoint. And actually, it's I started with a very skewed data set, but that's just because my data was originally divided in bin, and for this example, I didn't do it just to keep it a bit simpler. So you won't see like much unbalancing here, but I did start with, once I had bin data, I had bins where there were like a lot more O2s and, or a lot more LAEs, and so this is how this came about for me. And so there are solutions for that. You can think of alternative metrics. You can, like your classifier will report naturally precision, which is like the percentage of correct positive classifications. So, over like all the objects that are classified as positive, how many of those are true. Or the recall, which, I think of it as completeness, I guess, from my sort of more astronomy perspective, which is the ratio of true positive through the sum of like true positive and false negative. So basically, how many real LAEs have made it to my classification. I have been classified as LAEs. And this certainly help. So, these or a combination of these can certainly help. However, when we're thinking about this problem, we realized that, and this is something that James and I were discussing today, that what really matters is what you're trying to do with your classifier, right? That in some sense, I think that in just about every instance in which you are applying one of these machine learning methods to something, what you need to worry about is your end goal. Typically, you're trying to minimize the error in some quantity. And the error in some quantity may be like a non-trivial combination of all of these classifier metrics. And it wouldn't really make sense to optimize whatever algorithm, whatever model, according to a metric that then you're not interested in. So for us, for example, what we were trying to do was to minimize the error in the distance to these galaxies. And what the, it was, now, looking back, it seems quite obvious, but from the other HETEX colleagues, when they were thinking about this problem, they were like, oh, okay, here, what really, really matters is that we have as little contamination as possible. They were fully prepared to lose some completeness, meaning to have a lower recall score, because they thought, okay, we don't want any of the close by objects making the survey, because if we're then trying to measure clustering of things that are far away, of course things that are close by are going to be much closer together, and so we're going to mess up the whole thing. But instead, what we said is okay, is there a way in which we can quantify the error on the distance to these galaxies as a function of things that our classifier is going to spit out? Of course, the answer was yes, but it wasn't easy. So what we did is that we ran a bunch of simulated survey, and we used these techniques called Fisher metrics. Are you guys familiar with it? A little bit? No?
Probably them more than us.
Okay, are you guys familiar with it?
I remember James saying what it was, but I forgot what it was.
Yeah.
Okay.
It depends if that's, because we were talking about Fisher information, which
Right.
may not be the same.
Yeah. It's the Fisher information metric is what we're. So in this case, basically, it's a technique that can be used to sort of make, or at least we use it often when we want to be a simplified prediction of what the errors is going to be. So we're taking the likelihood function in the space of parameters, and we are just making the approximation that it's Gaussian, not in the observable, but in the parameters. And then you can compute the expected errors in every direction, so in every variable of your system, as the second derivative of your likelihood function, because if you assume that that's Gaussian, then basically the width of the likelihood function in each direction is the second derivative with respect to that axis. So what we did is we had a machinery that basically spit up the error in angular diameter distance as a function, using these Fisher metrics for any simulated surveys. So we made a lot of simulated surveys for different values of these two things, incompleteness and contamination, which were the two things that we could actually get from our classifier, because incompleteness is 1 minus recall. Recall is the same as completeness, and contamination is 1 minus precision. So this we could get from the classifier, and then we said, okay, let's run a whole bunch of simulations varying these two things.
Sorry, is precision what I'm used to hearing of as purity? Is that the same thing? What did you say? What is the 1 minus? What was the word you used for it?
Contamination. So yeah, if contamination is 1 minus purity, yeah.
Percentage positive, true positive. Oh,
So
yeah,
these are everything that has been classified as positive, and this is the one that were really positive.
So that is purity.
Okay, yeah. And it's for me, it's basically it's 1 minus contamination. So it makes sense.
How many of the positives are for real? So this
Many of the ones that are classified as positive are actually positive.
So this
Yeah.
is just a false positive, right? The way you've written it.
Why?
Because it's your false positives over the things that have been classified as positive.
It's still a fraction, though.
Yeah.
false positive is a fraction.
Yeah. It's fine. Go ahead.
Right? I think it makes sense.
There's
So.
different ways of saying this.
Right, but false positive I always think of it as a number. So,
Oh.
but yes, I think so. So it's false positive divided by the total amount of classification.
Yeah.
Yeah, because 1 minus this would be like false positives. Yeah. So it's a fraction of false positives. Yeah. Okay. Yeah, and so what we did is we said, okay, what's sort of like a functional form of a fitting formula in terms of these two things? And we said, okay, there's going to be a floor this is like for a perfect experiment, just because you have statistical error. If you have zero contamination, if you have total completeness, then you will have like this minimum amount. And then, sort of like for lack of a better way, we said, okay, let's have, like a power law with some coefficients of each one of these two things, and also a mixed terms. And we did a lot of simulation to find values for that fitting formula.
So do you have a one Fisher matrix for the entire data set, or one Fisher matrix per galaxy?
Entire data set, but this is the data set in this case is like basically what we know is like from our service we can find our observable in this case is the power spectrum, and we are actually looking at the derivative of the power spectrum of galaxies in different directions.
Okay, so you get all of the Lyman alpha emitters, which are distant galaxies, and then you so you classify them as Lyman alpha emitters. Then
Right.
you estimate their distances, and then you make the power spectrum, and there are 6, 7, 8 parameters in the power spectrum.
Well, this is actually in the power spectrum there are like like no parameters, but for us what we did is like we wanted to look at the derivative of like the power spectrum signal with respect to these two parameters x0 and x1. This is the error on sigma dA.
It's, okay, so we'll think of it as a signal error, like a Poisson error, like something that's just measuring how well you detected.
Well, so I think that I don't know how much in the detail we want to go, but basically what we had is like in, let me see if I can show you at least one thing of what the Fisher is. Yeah, this is like an example for something else.
Is it possible that we could pass the cookies around since we can't get to them?
Oh, yeah. I didn't see them, sorry.
We're normally allowed to. Thank you.
Oh, it's here, that's why. Who are you? So I guess that, like these, the Fisher matrix that we are trying to write down is actually meant to find the uncertainty in the measurement of the parameter distance. So in this case, my signal here would be the power spectrum, but the parameters have nothing to do with the ones that you saw there. The two things that I'm looking that sort of like that participate in the error are the error in angular diameter distance and the error in the Hubble expansion. So this is like a sort of like a purely cosmological thing. So what my Fisher matrix process does, and this was something that was done in the survey completely independent of our problem of classification, is having like the error in the distance and the error in the Hubble expansion at a certain redshift.
So sigma distance, is that for a particular galaxy?
Oh, this is for each of the galaxies in the survey. Is it? No, it's not true. It's like you built a power spectrum of galaxies in redshift bins, and this was at the median redshift of all those galaxies. So all the galaxies are at a redshift of between 1.9 and 3.5. Okay, so the way that they are bin in headtext is you first look at a redshift bin between 1.9 and 2.5. So you build the power spectrum of all these galaxies just by looking at how they're clustering together. And this gives you, from there, you can measure two things. You can measure the distance to like the median redshift of this galaxy, which is about redshift 2.2, and you can measure the Hubble distance, the value of like the Hubble constant. which is another cosmological parameter at redshift 2.2. So the Fisher matrix was used in the survey to make prediction on what these errors would be. Sigma angular diameter distance and sigma h. What we did is saying,
so that distance, I guess the distance then, since you're binning between redshift 1.9 and 2.5,
Yeah.
the distance estimate is definitely going to be in between those two values?
right, but you don't know it. You know the redshift, but in order to go from redshift to distance, you need a model of the universe. And this is what we are trying to avoid,
okay.
right? So that's why you need something independent. So, and so this is sort of like the cosmological part. What we did is to say, okay, in our, in our survey, in our like simulated survey from which we get this, we can actually now run a bunch of simulation for a bunch of values of contamination and incompleteness. In other words, we like sort of like injected in our survey a bunch of like false objects in different fractions, and this would be contamination, or we degraded the signal in the power spectrum by different amounts, and this was like simulation of different values of incompleteness. And then we found a fitting formula of the error in the plane of contamination incompleteness using that functional form.
So do you assume that the completeness and, I forget what you called the other one?
Contamination?
Contamination. Do you assume that those are redshift independent?
Do I assume that they are redshift independent? Yes, in the bins. So, the actual data, like here I didn't put any bins, but there, like we bin, and in each one of these bins, yes.
Oh, but you have a whole bunch of bins?
Yes.
Okay, gotcha.
All right, so this were to say that just like now, like a lot of work went into finding what was our optimal metric, and then we found basically coefficients for this fitting formula. And at this point, we knew, we were able to write the quantity that we wanted to minimize, which was like the error in the distance, as a function of, say, precision and recall, just to speak at least in more statistical terms. And here is where I learned that for me, another parameter that was really important to play with was the class weight. In other words, that even if at that point I had like not a particularly imbalanced data set, what was really convenient to do was to give a different weight to misclassification in one class as opposed to misclassification in the other class. So, and this was, our original intuition that perhaps we were more hurt by allowing O2 emitters in our survey, so by allowing close-by objects to make the cut, as opposed to like losing some LAEs because they were misclassified. But I think this was like for us quite an important parameter to play with. And I have an example. This is sort of like a really old plot, but for some reason I'm never able to make this plot work. So what you're seeing here is for like one of the cases that we had, the yellow and blue point I'll represent LAEs and O2 emitters. And here you have like the equivalent width, assuming that each one of them is an LAE. And here we have like the continuum magnitude. And so the data are the same in both cases, but this shows you the difference between using an equal class weight. And in this case, you have a class weight of 5 for O2 emitters, meaning that you are giving a 5 times higher penalty to misclassifying an O2 as an LAE. And you can see, how the decision boundary shifts, and compared to our like original line, now you do have features in here, and so you're doing. And this is also, a 2D projection. The actual boundary lives in like one more dimension, but of course for this, like I wasn't able to plot it.
And do you think this is equivalent to the oversample or undersample procedure?
Sorry, can you repeat that?
So if your data is unbalanced, so there's a technique called oversample or undersample.
I see. I've experimented a lot with that. I don't understand how this is really different from setting a different class weight. So for this particular one, I didn't, but other times that I've tried, this is just like basically like sampling more frequently, sort of like creating a new data set in which you're sort of like you account for the imbalance, right?
They call it case control sampling sometimes
Yeah.
in like longitudinal data.
I don't know what longitudinal data
It
is.
means like tracking the same people over a long amount of time, like in disease studies.
Okay.
Because you often have way more controls than you have cases in rare disease.
I see,
studies.
yeah.
So there's a sampler. So if you
Right.
wanted to look something up, case control is a good thing.
Okay, yeah, no, but yeah, I'm familiar with this. I just didn't, like for me, for example, I have like, using different class weights, I have like, undersampling or like oversampling on one class. And actually, I think that in scikit, if you put like class weight as automatics, what you will do is just assume that the class weight is inversely proportional to the frequency of that class, which I guess like is effectively, probably a similar thing to like oversampling a class for which you have just a few instances. So yeah, I'm like, yeah, I'll be happy to try. I just never understand, if there is sort of a conceptual difference that makes me say, okay, one is better than the other.
So if you use the class weight, so if you calculate the precision and the recall, do you include the class weight too?
Yes, I'm going to show you exactly, so you guys can also tell me if you think I'm doing well. And then I guess like two other, I don't know what happened to one of my slides, but it's kind of funny. So other things that I won't be talking about is like a choice of feature, is like it's just 3 out of 4, so it wasn't. And the fact that here it was really important to scale the features because the continuum was of the order like 10 to the negative 17, and like the flux in the line was of the order unity, and we actually see and I think that support vector machines are also well known for not doing well if your data really live in like sort of different ranges. So we saw very clearly the effect of scaling versus non-scaling. And then I guess I had another slide which was about, can I turn a classification problem into a regression problem? But somehow the text that I written didn't save, and so I have a slide that says, no, it does. On the screen, it just said problem. I don't know why. Oh well. And so,
you
yeah.
said you have only 4 features, right?
Yes.
But you have so few features. How do you choice of the feature? Because
Yeah, you mean like why am I bothering to choose?
Yeah.
Yeah, no, I mean, it makes a lot of sense, but the point is like 2 out of 3 are completely redundant because basically I have like the emission line flux, I have the continuum flux, and I have the equivalent width, which is like the ratio between the 2. So I actually don't want to use all 3 in case, having like 2 features that are basically like completely degenerate gives me problem. So that's why, but I still wanted to see if it made the difference to pick 2 out of 3, and in this case, which 2. So that's the reason. And so I also thought about this as, okay, like we started with just an idea, okay, this is a classification problem, but I also realized that another things that I could do with SVMs in Python, in scikit-learn, was to output, rather than a class, the probability of belonging to a class, which for a 2-class problem was also like, I think, similar to class weight. And so this is another thing that we explored. And basically you can, rather than saying, okay, the object is this or that, you can ask the algorithm to output a probability of being an LAE or an A2, sort of like a confidence, and then you can optimize for the threshold of your detection. And one of the reasons why I like that is that I think once you have trained your algorithm for that, and once your output is a probability, then if, say, the things that you're looking for changes, like if your metric changes slightly, you can still use this probability that you have derived and like reuse your algorithm right away. So again, I'll be happy to hear if you have thoughts on, sort of the relative merit of using different class weights versus, outputting a probability and then choosing the threshold.
It's not possible to make the power spectrum with galaxies that are sort of probabilistically assigned to as line.
Oh, no, you don't probabilistically assign. You just like output the probability and then pick what's your threshold, right? So in this case, what I would do is like probably, like if I don't do that, then objects which have a probability of like more than 0.5 to be an LAE will be an LAE. Objects that have a probability below 0.5, or actually the ratio of the probability is like, below 0.5, will be called an LAE, and the well, you get what I mean. Like, this is like, like my sort of like threshold that tells me like LAE or O2 would be like 0.5. But I could actually just say, okay, I optimize the threshold so that now, if I only call an LAE something that is an LAE with at least 90% confidence, then, I still have a two-class classification at the end. It's just that I'm getting there in a different way. Rather than having like a class weight, I'm having, I'm just saying, let me call LAEs only the ones for which I'm really, really confident. And then you still like keep going with your classes. Like you don't actually keep the probability. I think it would be nice also to sort of explore what happens next. But yeah, I don't know how you could build a power spectrum just with like a probability. Yeah. Other things you could. But the power spectrum in particular, I don't think. Okay, so I just wanted to quickly show what I've done here. So we have about 10 minutes, yeah? Okay. So please don't look at my programming, it's terrible. And especially because, it's easy, it still is.
You're very brave to show us it.
Huh?
You're very brave to show us.
I know, exactly. So please.
This is new stuff that's not published, whereas what you showed us before is already published.
Oh, this is the same thing. This is just the iPython notebook that I created with that. None of this is published. I presented it at talks, but none of this is published. So, I'm hoping that you won't publish it. But
Being videotaped.
Oh, well, that's true. I think it's okay. I've given enough talks, and slides are probably lying around. So.
The Samsung website's getting millions of hits.
Wait, but I thought you just
Oh
said
no? Oh, I would have never said yes to this invitation if you had told me from the beginning.
No, but in all seriousness, because I am really interested in this, I thought you just said this is discussed in your paper, no?
No, the paper is for the Bayesian method. The machine learning stuff never made into a paper. Like I've talked about it like at conferences, but
Okay.
yeah.
You have all these great insights. Can we get your slides in like PDF form? I don't want to.
Well, it depends. If you sign something, say, I'm not going to publish it.
Well, I don't even work on that. I just meant more the general insight.
Yeah, of course. Yeah, of course you can. And actually, I was thinking, if you guys want to take it as a project and sort of like bit my classifier, I would be very happy. I will have to check with the collaboration before, but if it's something that may be of interest to you, I would definitely be,
Well, no, actually, as I mentioned, I'm really interested in classifying AGN.
Mm-hmm.
And I just like your general insights about like how to approach
Yeah.
the error propagation and stuff.
I'm very, very glad to give you the slides. All right, so what do we have here? Well, this is just some importing stuff, defining some functions, blah, blah, blah. This is real data, so this is like our simulations and what they have. And
But you are going to publish this, right?
yeah, I guess.
That's awesome.
Thank you. I know, I want to, but I feel like now it's been nice to give this talk because it sort of like forced me to go back and look at this stuff and say I should really finish. But for example, the part where we created a metric, this was done for Andrew's student paper for the Bayesian method, so it wasn't yet implemented there, and I just did it yesterday here, just so that I could show you something that was current. But yeah, no, I should. It would be easy, right? No more work, just writing. Okay, so here I'm just like, okay, creating my data set, and then I can't remember why I did this. I sort of like made a function who like sort of exclude outliers, but then it's not implementing, and I don't know why. But like I can't remember why. Maybe it didn't actually make a difference. So this is like loading my simulation. So in the simulation, I have like 116,000 examples. But, and this is what, like for science, this is what I would use. But because I just like want to show how things are working, so you can also tell me if there are some like glowing mistakes, I'm just going to use like 5% of that, otherwise it just takes too long. And so here, this is a little plot of the objects, just like zooming in. This is similar to what we were seeing. This is like continuum luminosity, and this is equivalent width. And I guess that I didn't even write, but I guess that the red are O2s, so on average they have lower equivalent width, and the blue are LAEs, so on average they have higher equivalent width, like ratio between line and continuum. And you can see that there's not going to be ever a perfect classifier, because there's no way that this will ever be classified as an LAE, even if it is, and the other way around. But there's definitely like room for trying to disentangle a bunch of these examples. So here I'm setting this my like sampling fraction at like 5%. And what else am I doing? And here I'm scaling the data. And let's see. Okay, so my new data set has like 3 features, as we were mentioning, and just about 6,000 examples. And so this is like a function that I just wrote 4 of them very similar, because this was like today or yesterday. And so this is like my function that optimizes the parameter of the training set. And so in this case, this is like without using class weight. And so it's just like splitting and defining like the range of parameters. So these are like 2 values for gamma. This is like the soft margin. You don't need to try a lot of values. And this is the class weight. For the moment, I'm just like fixing at the value of 1, so it won't wander around too much. And this is like just a division in 4 folds for cross-validation. And this is really just a loop that tells me, okay, for each one of these folds, run through the parameter values, and for each one, create like 4 different folds and calculate what I called incompleteness and contamination, and then use that fitting formula to see.
That's the Fisher?
Yes, that's the one from the Fisher matrix. So remember that it was like, sort of, this was the floor that we found. Actually, this is incorrect, because this is the floor for the whole survey, which is the only value that I have. So now that I switched to a sampling fraction of I'm only using 5% of the data, the floor should actually be a higher value. So this is not correct, but for science it would be. And then I just look at the average score, where for score I just look at this like error in the angular diameter distance in like the 4 or 5 folds. And I select the model which has the best, like the lowest error. Make sense? Okay, so here we go. And this is the same thing, but with class weight. So I'm just giving a range of class weight, like 5 different values. I don't need to print the first time. These are like the things that I do to myself. Okay, so this is now like running on without using a class weight. And I've actually, in generating this sample, I've actually fixed the random seed. So for every classifier, it's actually selecting the same 5% just to, and I think that this is the right thing to do, right? Even if I select like different sets, I think that to compare different sort of flavors of the algorithm makes sense that the data are exactly the same.
Yeah.
Right? So.
Cross-validation? The folds in the cross-validation?
Not in the folds, but the 5% that I'm selecting, because I'm saying I'm using like a 5% scaled down simulation, but it's exactly the same for all classifiers.
Yeah, because otherwise you'd be classifying on 2 different sets of data.
Right, exactly. And so, yeah. So.
Where does the seed actually fit?
Say again?
I'm just trying to see where in the code the seed is actually set.
Oh,
Oh, it was
it's
earlier. Okay, never mind.
inside here you have like the train. Actually, no, this is how it's splitting the folds though also. Like the way that it's splitting in folds and test, I think it's also fixed. Like because I'm fixing the random seed here.
That's fine across classifiers.
Right. So here, this is where it's set. Okay, so this is just like 4 models, and it just gives me a result on the test set. And then I can do, so it's spit up something with, I guess, a gamma 0.01, and what else is there? And the soft margin is 10. And I can do the same thing, but now allowing the class weight to change, and this is actually going to take a minute or two.
While that's running, can I ask you, so
Yeah, exactly. Yeah,
the
perfect.
number of your class, I forgot the word already, the C parameter. So
Mhm.
you said you didn't need to, whatever the margin is.
Mhm.
You said you didn't need to check a lot of values.
Mhm.
Wasn't 10 on the edge of your parameter space? Like
Yes,
the edge
it's
of
true,
your
but
space?
I also have a note that says 100 never found to be a good option, so I have actually tried more than that. Just for this
Okay.
demo, I put it at 2.
Wait, what?
Oh, sorry. So you were saying here that this
Yeah.
C was like 10, and so 10 it was like, yeah, and actually with 2 this is, but you see this note like 100
Yeah.
never found to be a competitive option, so I've actually tested more values than that,
Okay, okay.
just for this demo.
Yeah, I just always get nervous when something comes
Is
back
yeah,
to the end of
yeah,
the space.
yeah. No, I mean I totally agree, and this is like the same things here. It's actually selecting 0.01, but like for science, I would
Yeah,
actually
right,
take a
right.
longer range. But here, just because I wanted to show you running,
Quickly, yeah.
I was like, okay, maybe we don't need all of that. And this actually, yeah, no, it's finished. And so in this case, like the error here looks to be a bit lower, and it's selecting a class weight of 3. But then, so I was like, okay, but this is still like for one possible realization. And so, my thoughts, and perhaps this is like where we could close and you guys can tell me what you think. So my thoughts on, how to estimate the error on this error. So, I want to find a way of saying, okay, if I had chosen another realization, or actually, yeah, I guess that this makes sense. If I now select a different like test versus training, like I think that I need to do that to evaluate the scatter, like the standard deviation in this value. Does it make sense?
Yeah.
Right, and so here, what I did is basically I've taken now different splits of training and test for my same like 5% fraction. And I'm just, and so, like once I've decided, okay, this is like my best algorithm, then what I do next is to take like 5 different splits. I'm just giving like 5 different random states, and to calculate the scores and look at the spread.
So when you say best algorithm, that's the best value of the tuning parameters? Or
When I say, sorry?
So when you say best algorithm, that's the best value of the tuning parameters?
Yes, exactly. What I've selected as,
And the one with the weights, right? With the
I can do it for both, but I think the interesting part is that this is the one with, is this, hold on a second, blah, 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 blah. Okay, so this is the one with the weights. And so I'm finding that actually the average error now, if like over like 5 different realizations, is 1.59, and standard deviation is about 0.02. And for the one with the weights, sorry, without the weights, because it's, yeah, okay, I found 1.61, and the standard deviation is lower. And so this was actually, quite a bit worse.
This is just over 5.
Yes.
Different things.
Should they be more? Like that's, I guess,
Well, 'cause
it's
it
a
seems-
question.
It seems to me that this is essentially trying to get at some kind of like Monte Carlo
Yeah.
approximation.
Yeah.
So I would think you would need way more than 5.
Yeah, I don't know. Yeah, you think that this is the
normally,
issue?
Yeah, normally if you want to run a Monte Carlo approximation that you want to have really any, I think it's going to have some accuracy for these kinds of things. We do like thousands of iterations.
Okay.
So I definitely think, because what's going to happen is that number will probably settle down and be a little bit closer to maybe what you had seen, or not.
Or not, because it's possible that that particular realization just brought a lower error. But what I'm saying is like, okay, the substance is fine.
Yeah,
I just like need. Okay. Yeah. Okay. Cool. And yeah, this is
Is it so when you compute the Fisher information, that depends on what the values of the parameters are, essentially what the power spectrum is?
Which parameters though?
You had the A through the G. And so the
A through the G are just parameters of the fitting formula. So the power spectrum has nothing to do with them. But I'm just saying, okay, the error on the power spectrum is something that I can predict, say, from theory, right? Because this is really done from theory. Then what I was doing is like injecting contaminants in my power spectrum, or taking away signal to sort of like evaluate the effect on the error of my contamination and incompleteness. And then I looked for a fitting formula so that I could actually write analytically how the error on the distance depends on these two things.
But that error on the distance, that dependence does not depend on unknown quantities like distance itself or the Hubble constant.
These are all marginalized over. So yes, there are parameters that go into the power spectrum, but I have marginalized over them, and I've left, I guess, the two only unknowns, these two things.
Okay.
So yeah, there's like the total amplitude of the power spectrum, there's a Hubble constant, there's the velocities of the galaxies, there's a bias. And these I've already marginalized over. So yeah, this made sense. So, I made learning curves just because, when I was like looking, okay, is it the problem that like the sampling fraction that I'm using is too small? But actually this seems like relatively well behaved. So I don't think I'm in a regime where, I don't have enough examples. And that was it. And then, I also tried the version in which I look for a probability, like I define a probability as opposed to just a class. Well, this would take far too long to run. So we can just see what happens. And so in this case, the decision probability threshold is 0.7. So this is telling me, yes, like you need sort of to privilege errors in one class over the other. It's another way of looking at the same thing. And this also I thought was like quite competitive with the others.
And this is still fitting a support vector machine. It's just giving you a probability at the end of the day.
Yeah. So the algorithm, it's just like this in it's just like a property of support vector classifiers in scikit. And then I just so it predicts a probability, and then I just created a little function that takes like the threshold and calls it like one or the other, and this is what my class is. So it's just like one extra step. And yeah, that's it. I think this is all I have. I think I bored you guys enough. Also, I'll be on my way to the airport. Thanks.
More questions?
Yeah.
Did you look at what's called an ROC curve? You know what that is?
Yeah. Not for this problem. I learned about that like I was telling James, like last summer I just took a summer off ASTRO and I just did like Kaggle competitions. And so this is like where I first learned this metric. But yeah.
I asked just because I know that you were kind of optimizing over the threshold, and so kind of it may be worthwhile to, when you're using that probability as its output, to just build a an ROC curve, I'm sure it's built into scikit.
Yeah, for sure.
Because that, I mean, generally in statistics, that's what we would do, is we would say, look,
Right.
here's this ROC curve, so there's no benefit over it, you know, to setting the threshold. I'm fine with the error at 70% or whatever, 0.7 or whatever from there, and then that's what they used to set the.
Like it's another metric that you're saying in general. It's a
and
good.
then area under the curve is for these kinds of classifiers. So this kind of regression style classification is what I work a lot with.
Okay.
And so area under the curve is a big thing that comes out of that.
Okay.
And then my other question would be, again, since I have to deal with this constantly, did you try, so rather than fit the support vector machine, it may be worthwhile just as a comparison to just fit a straight up GLM, like a generalized linear model.
Okay.
With like a code one of them as 1 and the other one as 0, the way that you've done here. And it's sort of very simple and super, super fast to fit.
Right. And maybe very easy to interpret what's going on.
Yeah, it's super easy because it's just a regression framework, so people really understand it. And I mean, I found, unfortunately, that it works super well. It's very hard to
I know what you mean. Yeah. It's a good question. It's a definitely like a good advice. Yeah.
Well, because definitely if you want to publish something like this, I mean, if I was reviewing the paper, my first question would be, did you fit a GLM? So it's at least something to think about, because it would go in the framework you've already written. It would just be like changing one line of code. So it's probably at least something to think about.
Right. Yeah. Okay. Do they also have the option of like sort of doing regression style? Because I still need something that sort of like helps me weight one errors in one class more than the other.
Yeah.
So here I had the weight to play with.
Yeah. So with GLMs, usually you can do that. There's some like probability weighting options that you can usually do. So like there's usually a thing where you can say weight this class whatever percent this class. I don't know.
Or I could do the oversampling or undersampling. I guess this is a way of doing it with any classifier.
Ways of dealing with it. I just don't know what they are. But they exist. Smarter people than I know what they are.
Great.
All right. Well, thanks a lot, guys. It was really a pleasure to meet all of you.